since the original papers were posted. So let me start at the end of the talk in some sense, which is what our results were. So you can see the two key results that I think we're going to sort of build up towards in the set of three talks are this particular result, which is a measurement of what the expansion history of the universe is as a function of redshift or look back time. And each one of these points out here corresponds to a measurement from DESI in the year one data, as we sort of work through each one of the various DESI samples out here. And the solid line here is just a fiducial lambda CDM line. It's not a particular fit, it's just I think it's the Planck lambda CDM line out here. So this was the key result that came out of DESI. And then of course you can interpret this result in terms of cosmological parameters. And this I'm largely going to leave up to Shadab to sort of expand upon in a huge amount of detail. But one of the reasons why the DESI results got so much interest and excitement was for the particular choice of constraining the dark energy equation of state, where you allow both the equation of state to differ from a lambda CDM value and also to have some evolution with time. The DESI, BAO plus CMB plus supernova results all seemed to favor a value with an evolving equation of state. And this, of course, got everyone very excited because, as in cosmology, we've been sort of looking very hard to see what the nature of dark energy is. And here was some evidence that this was not as simple as we had all thought it was. This is, of course, very early hints of these pieces. And as I said, I'll largely leave it to Shadab to sort of walk you through all what goes into the cosmological interpretation. And what I'd like to do today is unpack all of the details that go into the measurements of the distances that go into these cosmological contours, so that you have an idea of what went into these measurements and what all of the issues that we think are and why we think our measurements are as robust as we can. So to get started, the first place to start off is really, how does DESI do these measurements? And Shiva gave a wonderful introduction to this, so I'm not going to sort of repeat all of what he did, talking about baryon acoustic oscillations, but I'm going to give, just to sort of remind you of all of what he said. This is a standard ruler, so you basically have a fixed physical scale in the universe, which you can measure its apparent size at different redshifts, and measuring that apparent size gives you distances. Then you could go ahead and map what the expansion history of the universe is. And the standard ruler manifests itself in two different ways, depending on whether you live in Fourier space or configuration space. In configuration space, you see this feature in the galaxy 2-point correlation function at about 100 H inverse megaparsecs, or about 150 megaparsecs out here. And this is really the picture that Subha gave you was these acoustic waves that just get frozen into the universe at recombination, imprinting a distribution on the matter. And then once you've got that distribution in the matter, that becomes a distribution in the galaxies themselves. And so you can measure the 2-point correlation function of galaxies. You just take all the galaxies, you calculate distances, and you see this excess clustering. This was, of course, first detected in 2005 in the SDSS and 2DF surveys, and then, of course, in all of the future surveys out here. You can take this measurement in configuration space and convert it to a Fourier space measurement, in which case you get a sequence of these oscillations. And here you can see these BAO oscillations out here. So I will primarily show you configuration space measurements, but I will sometimes show you both the configuration and Fourier space measurements. DESI does the measurements in both configuration and Fourier space, and we get consistent answers across both of these. Now, one point to emphasize with baryon acoustic oscillations and why they make such a good standard ruler is the physics of baryon acoustic oscillations is exquisitely well tested by the CMB. The fact that we can predict the CMB acoustic features to the level of accuracy that we can is a statement that we understand all of the physics that's going into recombination and what's going on with the baryons. So the physics is there's very little wiggle room in the physics in baryon acoustic oscillations. And furthermore, the actual physical scale of the ruler is very well calibrated by the locations of the acoustic peaks in the cosmic microwave background. And so we have a ruler, and it's an incredibly well-calibrated ruler. And that's exactly what you want to do if you want to do very precise cosmological distance measurements with a standard ruler. I want to spend a minute or two giving you a little bit of just intuition for why this is such a naturally robust standard ruler. And it really comes down to the fact that this is a very large-scale feature in the galaxy distribution or the matter distribution. The feature, as I said, lives at about 100 H-inverse megaparsecs, or with the current values of H, that's about 150 megaparsecs out here. If you consider this scale and compare it to all of the other scales in physics, in sort of galaxy physics, the scales of nonlinear structure formation, which exist at the sort of 20 to 10 megaparsec scales, the scales of galaxy formation, which are even smaller scales, those scales are much smaller than this acoustic feature. And so all of those effects you might imagine will struggle to produce a feature on the same scale as this BAO feature. And so it's very hard to sort of mess up a feature when you've just got things at much smaller scales. Those things tend to have very smooth effects out to very large scales and don't actually change the location of the feature out here. And in particular, the further piece here is that all of these effects are actually just suppressed on these scales. So these scales are what would normally be considered sort of linear scales when you do these analyses. Of course, there are nonlinear effects, and I'll talk about those in a second, but they're very small. The second reason that this is a robust standard ruler is that this is a three-dimensional feature. And if you think about observational systematics, you have observational systematics that live in the plane of the sky, and you have observational systematics that live along the redshift direction, because those are the places you do the observations. You map out the sky, as Anand's pointed out. You do this by sort of mapping out in DESI with the legacy surveys. And then you go and get redshifts for some number of these objects. And so you would expect your systematics to live either in angular space or in the radial direction out here. If you need to produce a three-dimensional feature from something which is purely in angles and redshifts, the angles and redshifts need to know something about one another, because otherwise you will not get a spherical shell out here. And so in particular, there's that sort of conspiracy, of course, doesn't happen because the two observations are completely independent. And so it's very hard to mimic this with observational systematics. And I'll show you some quite extraordinary demonstrations of this as we go along. Okay, so this is a naturally robust standard ruler. You could ask, can we actually make this ruler better? And it turns out, and this will be important as we go along, that we can actually sharpen up this ruler. So let me walk you through what's going on out here. So let me imagine that we're past the CMB. We have a still very homogeneous distribution of matter. There's some small fluctuations out here, the sort of 10 to the minus 4, 10 to the minus 5 level. And let me just paint on for you, just as a toy picture here, this BAO ring out here with the central overdensity. Now let me imagine structure formation, and the inset here just shows you a profile of this BAO feature. The width of this feature is about 10 megaparsecs. So, right? Let me now imagine that structure formation takes place, so you can see the cosmic web starting to develop out here. You see sort of flows into overdense regions, flows out of underdense regions out here. And you see this BAO ring that we painted on here. This is, as I said, just a cartoon, but this BAO ring gets distorted. And this distortion takes on two things. The first piece that it does is it smears out the BAO feature. And this turns out to make the BAO feature just harder to sort of centroid on. If you imagine just a smeared out Gaussian, it's harder to figure out where the center of that Gaussian is. And so it's just the signal to noise of the measurement goes down. It also subtly changes the scale of this feature. And I'll show you some data from simulations that changes what that the overall shape is. So what you've done is you've very subtly, at the sort of percent level, changed the size of the ruler. Now, this large scale, these flows, if you imagine what flows led to all of this of course is 100 megaparsecs from one point from here to here. And so the scales of what's causing these are relatively large scales. These are not sort of 1 to 2 megaparsecs. These are 10s to 20 megaparsec scales. And so you can take this distribution of matter that you see, because DESI not only measures the two-point correlation function, it actually measures the full density field. You can take this full density field and undo the motions by figuring out what the sort of flow that gave rise to these fields are, and sort of put the BAO feature back in close to its original place. Never perfect. There's no way you can imagine, of course, doing this perfectly, but you can see you sharpen up the BAO feature. And not only do you sharpen up the BAO feature, but you also remove that sort of change in the BAO scale, restoring it back very close to its linear piece. And again, as I said, I will show you some examples of this in simulations from DESI. So this entire thing, and again, the reason you were able to do this was because the BAO feature lived on such large scales that all of the physics that was going on out here was large-scale physics, and you could undo some of these effects that led to some of the nonlinearities as we moved along. So all of this is sort of leading to the reasons why we like BAO as a standard ruler. It's naturally sort of robust, and then is made even more robust by our understanding of the physics that you have out here. Now, very quickly, what do you actually measure when you've got a standard ruler like the BAO scale? Well, you can imagine doing a couple of things. You can imagine taking the ruler and observing this BAO scale perpendicular to your line of sight. In that case, you're measuring the angular diameter distance, the co-moving angular diameter distance, over the BAO scale. So you're measuring an angle on the sky. And so what you're measuring is basically the angular diameter distance over the sound horizon, or the drag, very strictly speaking, the epoch of decoupling. But you could think of this as the same thing as the sound horizon for here. So you measure the angular diameter distance here. If you measure it parallel to your line of sight, then in this case, you're sort of measuring a difference in redshifts, and what you're measuring is the Hubble parameter at the redshift of that object. And so you get, whether you sort of orient the ruler perpendicular or parallel to the line of sight, you get a measurement of either the angular diameter distance or the Hubble parameter. And of course, if you measure at any other angle out here, you get some combination of those two measurements. You will often see BAO measurements shown in terms of an isotropic average measurement, where we sort of isotropically average the BAO feature both at all possible orientations to the line of sight. In this case, you measure this combination of the angular diameter distance squared times the Hubble distance out here. So the Hubble parameter distance is C over H out here. Right? The other version of this measurement, so you could either think of it as measuring these two quantities, or you could think of it as measuring this isotropic average, and the sort of complementary quantity to the isotropic average is measuring the ratio of the angular diameter distance to this Hubble distance out here. This is effectively the Alcock-Paczynski effect that you have, I'm sure, heard about, where you're taking a standard ruler and just sort of looking at the fact that the ruler has different sizes, perpendicular and parallel to the line of sight. And so you distort a ruler as we go along. So those are that's a very quick introduction to the BAO measurements. Key ideas here: you've got a standard ruler that you measure at different redshifts, which gives you both angular diameter and Hubble parameter measurements of things. Now, Anand has already introduced DESI in a lot of detail, so I'm not going to go ahead and do this, but I'm just going to pull up this slide that shows you the redshift range that DESI covers and the various traces that we get from the bright galaxy sample, the luminous red galaxies, emission line galaxies, and quasars, both used as tracer objects, and the Lyman alpha forest. And what I want to do now is sort of working outward in, so starting with the Lyman alpha forest, show you the BAO measurements from each one of these and dive into these into a little bit more detail so you understand where all the various pieces that came into that Hubble diagram plot that I started this talk with is here. So let's start off with the Lyman alpha forest. So the Lyman alpha forest, this is slightly different from the standard picture that you often see with BAO. Normally the story with BAO is told with the matter density field populated with galaxies. In this case, instead of populating things with galaxies, you use the distribution of neutral hydrogen and observed through absorption in the Lyman alpha forest. So you have some background quasar here. It's traveling to the observer. The light from the background quasar is traveling to the observer. It's getting redshifted. As that redshift hits the Lyman alpha transition, it gets absorbed by whatever neutral hydrogen there is, and the amount of absorption tells you something about the density of neutral hydrogen. This is sort of a good cartoon. This is not true that they're actual clouds, but a cartoon picture to think about here is that there are these Lyman alpha clouds that you're picking up along the redshift. And so I can take one quasar out here, and I can take another quasar out here, and I will see Lyman alpha absorption in two places out here. And of course, I can cross-correlate that Lyman alpha absorption, that the Lyman alpha forest now, or this neutral hydrogen, is just playing the same role as galaxies do. It's a tracer of the matter density field. And in the correlation function here, I can again measure the distance perpendicular and parallel to the line of sight and look for the BAO feature here. And here's a picture showing this BAO feature in the Lyman alpha autocorrelation. Of course, since everything is just is being used as a tracer of the matter density field, I can also do the other thing, which is I can say, let me take one of these Lyman alpha clouds and cross-correlate them with a quasar out here. The quasar, again, is tracing the matter density field. And again, I can get these measurements of the BAO feature. And again, you see this feature out here at 100 H inverse megaparsecs. And I'll talk a little bit more about some of the structures of this feature. So this is what a quasar spectrum looks like. Here's the Lyman alpha line. And here's everything blueward of the Lyman alpha line, which would get absorbed into the Lyman alpha forest as you sort of move from the quasar to the observer. And what DESI does is it breaks the spectrum into two regions, a region A, which is just things blueward of the Lyman alpha, but redward of the Lyman beta line, and then things blueward of both the Lyman alpha and Lyman beta lines out here, this region B out here. And of course, region B has a combination of both Lyman alpha and Lyman beta. The Lyman beta absorption, the Lyman beta forest, is at a different redshift, but there's Lyman alpha absorption also mixed into these lines here as well. This region out here is all Lyman alpha. And so you can imagine doing went the wrong way. You can imagine doing the following cross correlations. You can correlate the region A with region A. You can correlate region A with region B. You can correlate region A with the quasars. You can correlate region B with the quasars. And you can also do quasars with quasars. The number densities at the redshifts above 2.1 turn out to be low enough that the signal to noise is pretty low. We don't do these measurements. And in the Lyman, the lines that are blueward of the Lyman beta forest, you can cross-correlate them, but now you have to sort of disentangle both the Lyman alpha and the Lyman beta forest, and so it's complicated, and so we don't use these. So for these Lyman alpha quasars, there are 4 correlation functions that I will show you that come from the DESI data. So we'll get those 4 correlation functions, each of which will give me a measurement of a distance. And of course, I can then combine those all to get an effective distance measurement. Okay. So Anand said a lot about what the DESI sample is here. You've seen these, he's already shown you pictures like this. So this is the map of where the DESI DR1 quasars are compared to both the final DESI footprint as well as the SDSS DESI footprint. And this just sort of shows you the number of Lyman alpha pixels in DESI compared to everything else. And the number of pixels in the Lyman alpha forest is about twice as many as what we've gotten in 20 years of SDSS. And these are, of course, the DESI quasars and the SDSS quasars. So significantly larger sample. And so now let me show you actual data from the Lyman alpha forest. So here is the the autocorrelation in the Lyman alpha forest. I'm going to show these measurements. The Lyman alpha forest group measured a 2D correlation function, but I can then compress this down into correlation functions that are sort of perpendicular to my line of sight. So mu is the cosine of the angle to the line of sight. So this is perpendicular to your line of sight. This is mostly parallel to your line of sight. And then these are sort of two intermediate wedges out here. Now, if the shape of this correlation function doesn't look like the usual matter correlation functions that you're used to seeing, this is because the Lyman alpha forest has very strong redshift space distortion effects. And so that quite strongly distorts the signal out here. Furthermore, you also get in the perfectly along the line of sight pieces, you get spurious correlations due to silicon absorption features out here. This feature does not, of course, affect the BAO feature. It happens on smaller scales, but it is included in the fits that we do out here. And this, of course, also only occurs in things directly along the line of sight. So here are the four correlation functions that you get from DESI. And so these are, each one of these now, this is the A times A times B, A times quasars, and B times quasars, and then all split. And you can see a baseline model just shown out here. And you can, of course, try to locate where the centroid of this peak is, and then sort of move it back and forth. And you can ask what the distance is, and that's what gives rise to the measurement of the distance that I showed you previously. Now, one of the things you want to pay attention to very carefully is how well do we understand our systematics, and both in the galaxies, as I'll show you later, and as well as in the quasars, we spent a lot of time trying to understand what our systematics are. I'm not going to work through all of these various pieces out here, but this is a long list of various tests that you can do, either splitting the data in different ways or tests with the same data set but analyzed in different ways out here. And the key result is the BAO shifts in all of these cases. You can see no matter how I do the analysis, the BAO shifts don't move around by a whole lot, certainly much less than the statistical errors that we have for any one of these various variations, depending on all of as I said, lots of different variations. So no matter how you split up the sample, the Lyman alpha BAO results are quite robust to any of these measurements. And again, this should not be a surprise given what I had sort of the picture I painted of BAO survey, of the BAO feature. Moving from the Lyman alpha forest down to lower redshifts, now we sort of move into sort of galaxies or point tracers of the matter density field. And DESI has 4 tracers that it uses in this region. As Anand pointed out, there's the bright galaxy sample, the luminous red galaxies, the emission line galaxies, and the quasars. We break these up into redshift bins. You can see these marked by the various dotted lines. And so we have 6 redshift bins. The quasars are very low number densities. They're analyzed in a single redshift bin out here. One point to make about the DESI data is you'll notice there are also regions where we have overlapping samples. In particular, from 0.8 to 1.1, we have both LRGs as well as ELGs, which allow us to do internal consistency checks within the data itself to see, do we get the same distances? And in fact, we do get the same distances, whether we use the LRGs or the ELGs, or we can, of course, use the combined sample out here. The sample I'm going to show you uses 5 points. The sample I'm going to show you that gives rise to the results that I'll show you in a few minutes has about 5.7 million unique redshifts covering an 18 cubic gigaparsec volume. It's about 3 times the volume of the Sloan Digital Sky Survey. So let me just highlight some of the features of our analysis. This is the biggest data set, and every data set is almost always the biggest data set, but currently this is the biggest data set, both in terms of numbers as well as the volume. One of the key improvements in the pipeline that we did was we've actually implemented a catalog level blinding scheme to avoid any confirmation bias. So when we did our analysis, we actually moved and perturbed the positions of galaxies so that the correlation function is not sort of what you would naturally expect. This meant that everything was consistently blinded. So the RST measurements, anything which was a cross correlation, everything was blind to this. And so we had this catalog level blinding scheme. And until we were certain of what our full analysis pipelines were, what our systematic errors were, we did not unblind our data. So we unblinded our data last December, and then the results we basically were, the rest of the time was spent writing up the results out there. So there's no tuning of the data to sort of after we got our results. The other piece here is a unified pipeline. So DESI, because we now have samples at multiple redshifts, we can analyze them in exactly the same way over all tracers and all redshift slices. We have consistent models in Fourier space as well as configuration space, so we can make sure we get exactly the same answers, and we know we're comparing exactly the same models in both spaces out here. There have been a bunch of new enhancements to the BAO pipeline that have been sort of motivated from thinking about the physics that goes into the BAO feature. There have been some improvements to the reconstruction techniques that I showed you. This combined LRG plus ELG analysis, and all of this drives into a very comprehensive systematics error budget that I'll give you a flavor of. Now, as I said, there were 6 redshift slices, and I could start showing you correlation functions and power spectra of all of those 6, but we'll be here for another couple of hours. And so let me just show you a couple of examples of this. So here is the correlation function of one of the LRG samples. This is the high redshift LRG sample out here. The solid colored lines are the data. The dotted lines are, the solid lines are post-reconstruction. Those are our default measurements. You can see the pre-reconstruction lines in dotted regions. And the black dotted and black solid lines are what we get from our simulations of the DESI data. Shadab was instrumental in sort of making some of those simulations come together. And here's the same thing in the power spectrum now for the ELG sample out here. It's a little hard to see the BAO feature in any of these measurements because, of course, there's oscillations and things like that. And so what we often do is we divide out or subtract off sort of a smooth piece out here just to highlight the BAO feature. And so for the same 2 sample or slightly different samples, here are the BAO. Here's the BAO feature in the correlation function space. The measurements here are both for the monopoles, the angle average correlation function, as well as the quadrupole. The quadrupole is sensitive to the ratio of the angular diameter distance to the Hubble parameter. The monopole is sensitive to the dV factor that I said. And similar measurements, you can see these clear BAO oscillations in the power spectrum out here. So let's dig into these BAO features in a little bit more detail. The first thing to notice is that the BAO feature for all of our samples are very significantly detected. So this is a slightly complicated plot. So let me just walk you through what's going on. Let's just pick one of these samples. Let's pick the LRG plus ELG sample, which is this purple line. This is just showing the likelihood of the distance measurement, now measured in sort of some dimensionless unit or ratio of what the sort of expected dV over RD ratio is to some fiducial value out here. So this is just telling you how good your distance measurement is. And you can see, there's clearly a minimum in this likelihood telling you how well you've made your distance measurement. The corresponding dashed line out here is a model with no BAO feature. And so you can look at the difference in chi-squared between the two to get a rough idea of what the significance is. And you can see in this particular case, it's from the figure itself, you can see it's just over 8 sigma. It turns out to be about a 9.1 sigma detection of the BAO feature. And you can see that for all of our samples, we run from the lowest, which is about a 3.3 sigma detection, all the way up to this 9.1 sigma detection of the BAO feature. So BAO feature is very clearly detected in all of the samples. If you just ask what our aggregate distance precision is, and of course this is not what goes into a cosmological analysis, but this just gives you sort of the rough idea of what the overall aggregate precision is. Our aggregate precision is about 0.52% out here. Just to compare the SDSS over the 2 decades got an aggregate precision of about 0.64%. So already in about a year, we have our aggregate precision is much better than that. Let me now dive into some of the theoretical systematics that go into the BAO feature. So the first one, this is in a paper led by Stephen Chen and Colin Howlett. They sort of looked at the BAO feature theoretically. As I said, this is a large-scale feature where you can really treat a lot of things perturbatively. And so you can just go in and say, what does galaxy bias do? What does sort of nonlinear structure formation do? And you can work out various templates. And all of those templates you can see have these little oscillations in them, which can shift the BAO feature. You can't quite see this in the figure caption, but all of these are actually sort of, to make them all comparable to the BAO feature, you have to sort of multiply them up by some large number to actually see these effects out here. So these are sort of percent level effects. You can ask what these effects would look like. This is all, of course, pre-reconstruction. You can ask what these effects would be post-reconstruction, and post-reconstruction, these effects get even smaller. To sort of show, and so you can go through all of the sort of known lists of systematics that you have, and you get systematic errors. We can sort of put down a systematic error for each one of those effects based on what we think we know. And depending on the system, for the total combined systematic errors turn out to be about 0.1% for this isotropic DV measurement and about 0.2% for this Alcock-Paczynski measurement. You can do this totally theoretically, but I can also try to do this in simulations. And so I can take a simulation, I can put down my best guess of luminous red galaxies, which is one version on the left, or emission line galaxies, which is the version on the right out here. And I can ask, what is the distance measurement that I get? If we were getting an unbiased distance measurement, we would get something that's centered around these dashed lines here, or the solid line here. So sort of 1, or in this case, the deltas here shown as 0. And you can see that pre-reconstruction, there's actually a shift. It's about a 0.5% shift, and this is not surprising. You expect these shifts just from nonlinear structure formation. You'll notice after reconstruction, though, these shifts all go very, very close to 0 out here. So there's basically no shift in the acoustic scale, or basically the standard ruler is the sort of linear theory standard ruler predicted by the CMB out here. There's a lot that goes into these measurements, and I'm happy to sort of answer questions about all of these. This is work that was in 2 papers, one by Christian Garcia Quintero and one by Juan Mena Fernandez. Another thing that goes into the BAO measurements is to say we need to assume a fiducial cosmology to actually calculate a correlation function or a power spectrum. And the answer here is it basically makes no difference. You can see a whole range of different fiducial cosmologies, and none of them make any difference to the fiducial cosmology, except one of these, which is the C003 cosmology. You'll notice involves there's a little bit of a shift out here. And this is because this actually involves a non-standard and effective. So you imagine there's some more relativistic degrees of freedom, which changes the acoustic scale. If you account for that, this was a large effect in the simulations that we looked at and this particular cosmology. If you account for that, you again remove all of these effects totally. And then finally, to do the analysis, you have to know what your errors are. And we have sort of looked at a number of different ways. This is often the most computationally time-consuming part of any of these analyses. And we've used both a combination of sort of analytic covariances as well as covariances from mock catalogs, and we get exactly the same answers whether we do the analysis with an analytic covariance matrix or with a mock covariance. The use of the analytic covariance allows us to sort of tune our covariances exactly to the observations, which mean our error bars are actually consistent with the actual observables, which is much harder to do with a mock covariance because, of course, you're not going to regenerate all of the mocks out here. I promised you I'd give you a little bit of a picture of the fact that the observational systematics are subdominant. And so what's shown out here are 2 samples, one of which is the actual sample that we use, this weighted sample, these filled circles. The other one is a sample where we basically don't try to correct for any of the observational systematics that we know. There's a whole number of them, from things like the effects of stellar density, calibration, etc. And you can see the BAO scale, again shown in this alpha ISO or alpha AP, is basically unchanged over any of these samples, whether you go from the sample where we've put in our corrections as we best know it, to a sample where we pretend that there is no correction whatsoever. And you see exactly the same answers out here. Again, no surprise with this picture that you have that the BAO feature is a three-dimensional feature, which is very hard to sort of mimic in 2 dimensions. So here's our systematics error budget. I'm not going to read through all of these. We have them for the various systematics as well as the various tracers out here in different pieces. The net takeaway here is our statistical plus systematics error budget. The effect of this is to basically inflate our statistical errors by about 5%. So the statistical errors are very, very small compared to the systematic errors are very small compared to what our current statistical errors are. So you could take all of these BAO results and ask, are they consistent with one another? There's lots of ways to ask consistency. And so let me just tease you a little bit with this slide. I'm sure Shadab will show this in more detail here, but this is saying for each of the BAO samples, what is the constraints on this for a lambda CDM cosmology? What is the constraints if I sort of vary omega matter and H naught times RD? Now the BAO by itself is, each one of these is just a single distance measurement. There's no combination of CMB, and so there's a degeneracy in this plane. But you'll notice that all of them, if you plot all of them out here, from the BGS to the LRGs and the various samples, they all sort of intersect on a cosmological model, which is basically consistent with what we see. So internally, all of the BAO measurements are all consistent with this lambda CDM within a context of a lambda CDM model. You could ask whether our BAO measurements are consistent with previous measurements that have been made. And so here is the redshift less than 2.1 Hubble diagram. The colored points here are the measurements from DESI, the year 1 data. And the gray shaded points are different measurements from previous surveys, and they're all listed out here. The key ones I want to sort of highlight, the key things I want to highlight here, again, this is the isotropic distance measurements. And these are the Alcock-Paczynski distance measurements measured by the monopole and the quadrupole out here. 2 things to note. Firstly, the solid line here is not a fit. It's just the Planck lambda CDM model. And it would be sort of interesting to compare in the regions where we have overlapping data with the SDSS galaxies with the DESI galaxies, in particular the luminous red galaxy sample. And you'll notice here the SDSS galaxies, there's a little bit of a discrepancy out here, and then there's a discrepancy out here and with these points out here. So I'm going to dive into this discrepancy. The first thing to ask is any of this coming from the changes to our pipeline? Oops, went the wrong way. And so we went back and reanalyzed some of the SDSS data. We started with the fiducial data out here, and then we worked out the published data. We analyzed the actual correlation functions that came out of DESI, out of SDSS, and then we actually went back to the catalogs and analyzed them with the DESI sample. There are small changes across all of these, but you'll notice that they all basically lie exactly on top of one another. So let's come back to this point here. The biggest discrepancy turns out to be in this measurement out here, in this and the angular diameter distance here. This is about a 2.7 to 3 sigma discrepancy at about redshift 0.7. It turns out the 2 samples at this redshift are pretty uncorrelated. The cross-correlation coefficient is less than about 0.2 out here. We've looked at this in a bunch of detail, and as far as we can tell, we see no reason to believe that this is anything but a statistical fluctuation. Of course, once we get more data with the year 3 sample, we will come back and revisit this measurement. Again, this is a good point to sort of emphasize. This was a completely blind analysis. That we weren't trying to match the SDSS data. We just took the data points as they lay. You'll notice also, though, that the redshift 0.5 point is off, and so let me just point out this other piece, which you could ask: are all of the weird results coming out to this 0.5 point? And the answer is no. If you take out all of the DESI points below point 5 and replace them with the SDSS points, you get exactly the same cosmological results. So our cosmological results aren't coming from these fluctuations that you're seeing. Okay. So sorry, I've gone a little bit long, but let me sort of end back by ending back onto this Hubble diagram out here and show you the Hubble diagram as measured, or the expansion history as measured by DESI. I will leave it to Shadab to walk you through all of the cosmological consequences of these measurements. But so far, as you can see, they're exquisite measurements, sort of a 0.54% aggregate distance measurement over this entire redshift range. And this is, of course, only year 1 data. And as Anand pointed out, we've got year 3 data in hand. And we're so stay tuned for our analyses of year 3 data and beyond. So let me stop here and take any questions. Thanks.
Thanks a lot, Nikhil, for that detailed talk. Do we have questions? Shabir.
Hello. In case of BAOs in CMB, gravitational lensing smooths out those peaks, right? So is gravitational lensing effect important for BAOs in galaxy surveys?
At these redshifts, no. The redshifts, these are shallow enough that so the gravitational lensing effect is pretty small. We have it in our systematic error budget, but it's small for these samples. Right. As you go to much higher redshift samples, yes, you'll start to worry about it a little bit. It doesn't actually bias your result in any way. But you can. It's very easy to put into the template.
Thank you.
I had a question about the 4 kinds of matter tracers that you have been talking about. So is it that you divide your line of sight into 4 different redshift ranges, and in each range you pick one kind of galaxy? But if so, what is the rationale for that? Because quasars are basically accreting supermassive black holes, and emission line galaxies also could be either accreting supermassive black holes or starburst galaxies. And your what did you say, luminous red galaxies, I believe, they could also be accreting supermassive black holes, but without emission lines and so on. So I just wanted to know what was the rationale for these different choices.
Yeah, that's an excellent question. So maybe I'll come back out here. So this is the, so these are the redshift bins that we use, and you can see the redshift distributions of each of these objects in this range. So a lot of it is defined by what's the best way to select galaxies in the appropriate redshift range. So
your screen is not shared. Do you mind sharing?
Oh, I apologize. I somehow lost that. Let's do that again. Okay, can you see my screen now? All right. Okay, should be shared now. Let me know if it isn't.
Yeah.
Good. Okay. So right. So this is the redshift distribution of the various traces that we have. So you're absolutely right that these words that we use, luminous red galaxies or emission line galaxies or quasars, they're not sort of unique, sort of clearly well separated samples of objects. A quasar could also be an emission line galaxy. So most of this is really defined by how we select our targets. And a lot of these selections for different redshift ranges, they're just different ways in which you can effectively select objects to make sure you've got objects in that redshift range and not in some other redshift range. So for the red galaxies, for instance, you look for something with a large 4,000 angstrom break, and that's what we define as a red galaxy in this region. For the emission line galaxies, it's a set of color cuts that you say, okay, this is reasonably likely to be a star-forming galaxy with clearly detectable oxygen doublet. Quasars, you use a different set of pieces to go after the quasars. You'd look for things which are point sources. So we're not claiming that these are sort of independent, totally independent and sort of, unique samples. They're just names to give objects that you can use to trace in different regions at different places. And you can see, the efficiency of some of these algorithms works better at some redshifts and worse at others, right? For the red galaxies, for instance, it drops off very quickly as you get past redshift 1. Quasars are very hard to find. The emission line galaxies, we really are trying to get galaxies out in this redshift range. That sort of answer your question, or I'm happy to sort of clarify further.
Yeah, I think that helps, right, Padmanabhan? Another question.
So I think in your delta chi-square versus alpha S plot, right? So it's very frequentist, and I think cosmology shifted to, I thought, Bayesian analysis long time back. So let me ask a specific question on that. So there are also other parameters. So do you marginalize over the other parameters when you do the delta chi-square versus alpha S plot, or do you use profile likelihood to take the maximum values of the other free parameters, which is what I think particle data group recommends?
Yeah, so when we do our fits, so this is of course just to give you a sense of how strongly the BAO feature is detected. When we do the fits, we actually marginalize over all the parameters, and in this case too, we've marginalized over all the parameters. So this is sort of this is a delta chi-squared, but you can think of it as sort of a delta chi-squared think of this as a difference in the likelihoods. So we have marginalized over all of the nuisance parameters.
Hello. Yeah, I have a question. The kinematic redshift component in whatever distance measurements we make, how they will affect this BAO signals in the analysis?
When you say what you mean is sort of how do the redshift space distortions affect the BAO feature? They distort the BAO ring, so you don't get an isotropic ring anymore. We can put that effect into our analysis, and we have a rough shape of what things are. Now this is very large scales, and so linear theory turns out to be a very good approximation to how it affects things. So you can ask, what does the Kaiser effect do? I should say, when you do reconstruction, you have the option of removing some of these redshift space distortion effects as well, because you can, the same displacement is proportional to the redshift space distortions, and so you can try to isotropize the BAO feature. That's what pretty much every survey until DESI has done as its default. We chose to actually not remove the redshift space distortions in our analysis because it turns out that it actually improves the fits. We can theoretically show that you sort of get much better fits to the correlation functions. But whether we do it or don't, you get the same answer.
Yeah, thank you. And another question is related to the evolving dark matter, which is one of the result of DESI. So is it estimated with the Bayesian analysis, and if so, by what base factor it is dominant over the constant dark energy model?
Let me actually defer that question to Shadab when he sort of dives into his. So the numbers are in the paper, and I think it is sort of moderate significance is the sort of Jeffrey scale numbers, but I'm going to defer that to Shadab's talk.
Sorry, so when you are showing this cross correlation between high redshift stressors, for example, Lyman alpha and quasars, there I could see like in the correlation length, there are like 2 peaks for cross correlation, right?
This one?
For Lyman alpha, yeah, for Lyman alpha and quasar, yeah. So why, first of all, intuitively, why is that, and how do we measure acoustic peak from like this 2 peaks, like standard ruler from this?
That's a great question. So the second peak is coming from silicon lines that are in the same region. You can understand what that silicon line is by sort of also, you can understand the contamination And you can figure out that this is a silicon line by sort of looking at things redward of the Lyman alpha forest and using that region, then seeing the silicon line there. This really only comes in the sort of very close to line of sight measurements out here. And we can put this into the model. Again, I'll notice that the scales out here are actually quite different. The angular scales here are very small angular scales, and you can sort of isolate the BAO feature. And this really just comes into this particular case, but of course you can put this into you basically fold this into a model, because we know what that's coming from. It's the silicon lines, and so you sort of say, trace the silicon as a tracer, and then just go with that.
Very nice talk, Nikhil, as usual. So the BAO results are at 6 different redshifts, but the tracers span a wide range of redshifts. So you must be doing some weighing. How robust is this weighing, and how do you do it?
Yeah, so excellent question. So Shubha's point here is that, let me pull up a slide here. That, we basically looked at sort of give you one measurement for each of these 6 points, and clearly there's a range of redshifts out here. So what we do here is basically quote this at some effective redshift, where the effective redshift is just the sort of pair-weighted position of the peak. The systematic error budget actually includes, how much things would vary across this line of sight, and how much things would change. And the answer is it doesn't change a whole lot, and you can sort of treat this as some effective piece. I should say that we're not saying all of the galaxies are at the same redshift, right? So what we are doing is really saying we've got some. Maybe I'll try to go to a different slide and then sketch it out with my thing, right? You've got galaxies as a function of redshift out here, and at each one of these redshifts, I assume some fiducial cosmology to convert redshift into distance. So it's not like saying everything in the 0.6 to 0.8 slice is at some effective redshift. I'm converting all of those, and then what we're saying is we've got small corrections from that, and so you already are at small deviations, and so there's just some effective scaling of that redshift, and you can think of it as an overall scaling of the position, then some derivative scaling, which is the Alcock-Paczynski term. So this is an effect, and we certainly have ways of sort of breaking this down, but it's a very small effect for any of our measurements today. And as we get more data, we'll break it down into smaller and thinner redshift slices.
Hi, thank you for the nice talk. You briefly showed a slide on the equation of state, W0 was WA, and there was a data set with the fit of Pantheon Plus, which seems consistent with W0 minus 1 and basically standard cosmology. So what is driving the fit towards the standard result?
So I should say, again, let me largely defer this to Shadab's talk, but I'll say, most of the, there is some variation depending on exactly which supernova sample is. And I'm not a supernova expert by any means, so I'm not at a position to sort of tell you all of the differences between sort of the Pantheon Plus and Union 3. The DESI supernova 5-year sample is a photometric sample, so I do know that, and so that's a real difference between the two. There are clearly overlapping supernovae in the Pantheon Plus and Union 3 samples, but they're the analyses are different. At this point, the most we can say is these are sort of tantalizing hints of something, but we're clearly, as we get more data, we'll start to get at least a better handle on what all of these pieces are. The BAO results by themselves, if you take the BAO results, or you take the BAO results with the CMB, are consistent with the lambda CDM model by themselves at less than at the 3 sigma level. There's again hints, the best fit value wants to live off slightly off that plane, but everything, but they're certainly consistent.
Thank you.
So for the
But again, I think Shadab will dig into all of these various pieces in his talk later this afternoon.
Thanks, Nikhil. So very quickly, previous to talk, I forgot to ask any online audience if they have any questions. You can unmute yourself and speak or raise your hand. I don't see any. Okay, so maybe we can stop here. Thanks a lot, Nikhil, again for answering all the questions.
Okay, thanks very much. Bye.